So good morning, everyone. My name is Martin Ruta, and I would like to invite you today for my 5th webinar in 2022, where we will talk about the arc flash mitigation solutions. And the purpose of this webinar is to show you the example of project we did together with my colleagues. I'll introduce them. Few words about me. So of course you can find me on LinkedIn if you want. I'm doing the last 10 years power system studies and arc flash as well, and in overall 15 years in electrical engineering. But feel free to go through my LinkedIn profile. You will find it's up to date. You'll find everything there. Few informations about the webinar for today. So I try to keep it under 30 minutes. We will have a Q&A session at the end. Usually it's like 15, 20, 30 minutes, but it depends when we'll run out of time. And I'm recording this, as you can see, and I'll upload it later on my YouTube channel where you can watch it. And if you subscribe to the mailing list, you'll get the email with the summary link, everything else. What do we have for today? I will just simply go through the project, give you an idea what you did and what we plan to do, some conclusions and questions and open points, and then we can jump into Q&A. So let's go with it. Project overview. So just to give you background, this is a digital twin of the installation that I work with. And of course you cannot see the details because this is a real project and I changed the names, but it's the real customer. So what we did, so this is an industrial facility. They had two transformers, one supply from medium voltage, multiple bus ducts, as you can see. So there's the main one and multiple bus ducts at the production floor. And they generally change everything to new. So this was completely retrofit, or not even retrofit, it was exchanged. So they replaced this whole part of the system from transformer down. I created digital twin in SKM in this project, ran all the report, and idea was, okay, when we can improve it. So you might recognize this slide from the previous webinars I did. We discussed all of this before, so I'm not going to repeat it. Just to tell you that we are focusing on providing the recommendations and improvements for this project. So that's the whole idea behind this webinar for today, to show you what I did, why I did this, what effect it has on the system. So provide site-specific recommendations. If we are in the recommendation, you probably remember this hierarchy of controls. So this is going by an FPA70E, different levels of decisions that you can make to improve your safety, generally from most and to least effective. What we'll be doing today is going to find out if we can do anything around the substitution elimination. So if you can reduce energy to very low level, or we can maybe reduce it so to make it workable, but this is what we are going to find out. If I go too fast, let me know later. So what we proposed solution, what was proposed. So you've seen this in the webinar number 4, when we discuss in more details about the mitigation solutions, because there are a lot of options that we can choose. For this project, we mainly focus on overcurrent settings improvements, which is a base, I would say, and also on the arc flash relay. And now we'll explain this in details. The rest was not really possible to do, and the reason for it was on the next slide, because it was already done. So I joined the project and I was asked to make the arc flash study at a point when it was already done. Everything was exchanged, rebuilt, almost finished. And typically I did, as normally we do, all the short circuit protection, selectivity study, equipment evaluation, and arc flash. Arc flash was the biggest issue, but also the selectivity was a big problem for it, but it's not for today. So that was the whole system. The brand new switch gears for the low voltage, And this is the motor operated clutch on the main bus duct. So that was a surprise for me that it's motor operated. Everything below transformer was rebuilt, and I joined in the point where every hardware was already in place. So that's why we have a limited choice. But that's how it looks like. So the first thing, we always identify what's happening as it is. So this is existing situation. And I will jump in it. We don't discuss details, what I did, why I did. You might revert back to the previous webinars. But you immediately see the line sign of the main low voltage panel is a problem because it's almost 50 calories per square centimeter. So this is something we have to fix. The bus side, which is behind the breaker, I'll show you. It is something approx 12 calories. And the bus duct, which is below, is a kind of surprise because it's almost above 17, almost 18 at some point. So this is something that can be tolerated, but we will improve it. And this as well. You might ask about the medium voltage part, but because it was not on the customer scope, so technically didn't have access to it, and it was internal arc classified, we just ignore it because we don't have any influence on it at this project at least. To give you a summary, that's how I'll show you each slide. So that was existing settings. Those are the results that we have. And I use color coding so it's more visible, so you can actually see the difference. Important point is that there are no updates, so this is as it is, as built with existing settings. The clutch, which was on the bus duct, is normally open because that's the normal operation of the system. So the first solution, as I mentioned, was overcarrying settings. You might have a look. So this is a time current curve, so the graphic representation of the overcarrying settings of the medium voltage fuse, low voltage breakers, and some kind of, this is a feeder from the main bus duct. And this is existing, this is my recommendation. Because we had some limitation in the system, mainly because of the medium voltage fuse, which is not selective with anything else here. Here is not selective, and here is not selective either. But I make it a bit faster, and I try to maintain selectivity under arc flash and some other locations, which should work. But that's the limitation from the hardware point of view, which we have when the project is already done. Yeah, there's nothing I can do with this. I can provide recommendation to replace it, but you can imagine this is a new switchgear that is already paid, and now you have to replace it. So we will talk about it later in conclusions. You might see what I highlighted here, that technically it is selective under arc flash, but it's not selective under normal short circuit. And this is purely situation because we have the medium voltage fuse, which I cannot change because it's generally okay from every point of view, from the design point of view, but it's not good from protection point of view. So did it help? Yes, it did. So I was able to, with the settings as we provided, I was able to change the bus side, so generally the switchgear behind the breaker, from 12 to 6, which is okay. And the bus duct itself, we dropped from 70 to 3, which is very nice. That's a big difference. And this is only the settings improvement. So let's say quite cheap solution. Good. The next one was arc flash relay. So because I know people from Arctech, I work with their partner in Poland, which is Miłosz Morawiak from NV Project. I think he's supposed to be here today. I generally decide to propose arc flash relay as a good solution for this system. And as you can see, there was some settings improvements, so you can see the difference. And I propose arc flash relay as a second one. So to fix the line side, which is still 49, 47 calories, which is too much for this customer. So just a few words about what is arc flash relay. So I call it arc flash detection system because it detects arc flash in where we have a sensors. So we install the sensors in specific fields. We have a unit which is main. Sometimes we have an extension unit. They detect it very fast. So all the processing is below 5 milliseconds. I think it's 3 or 4 even or less. So it's extremely fast, and then it has to send the trip signal back to breakers. In our case, also to the medium voltage coil, so we can de-energize the system. And that's it. So that's, I would say, it's, keep it. There's a lot of complicated things behind it, but generally the topic idea is quite simple. So we try to lower the time and lower energy. And I will show you the video that I got from Arctech, which is very nice, show the difference between each system. Let me show you this. So I hope you see on the left side we have a system without protection up to 300 milliseconds. In the middle we have system with arc flash relay, which was 62, 63 milliseconds, approximately what we calculate in our project. And on the right side you have arc quenching, that we'll talk a bit later. And that's a great thanks to Mikko Maninen from Arctech that he was willing to share it with me, so I can show it to you. I did some calculation for it. So from the data from the test they did, I recalculated back that there's supposed to be something around 10 calories per square centimeter. The one with the arc flash relay was approximately 2.1, and the one with arc quenching was 0.1. So generally this was below 1.2 calories level. So we will not need arc-rated PPE to work around this equipment. Okay, so once again, great thanks, Mikko, to share this with me. Idea about the system. So I would like to show you what we did and why I think it's the best solution for this project. So you can even see the labels I put in, the red one, which is above 40. That was a part of the system. There was a bigger rest of the feeders here. So you can see the main unit for the arc flash relay was installed here. There was extension unit hidden behind the doors because there's nothing really to do with it. There are multiple sensors, so more than 3 actually, but I show you this one. So we installed the, let's say, flash sensor, so light sensor. Here we installed the light and pressure, so flash and pressure. And again, the sensors on the other specific places in the system. And those are the details that I really leave to for the Arctech and Miłosz Moravek from the NV project, that he was handling all the detail engineering. Great thanks for help once again. A very important part here is that it has to communicate with the low voltage breaker, which is the main breaker in the low voltage switchgear, and also to the medium voltage switchgear. And that's important because otherwise we cannot improve the line side of the breaker here. And just to show you the results. So we were able, with this kind of system, because we installed it in the both switchgears, to drop from 49 to 2.4, 2.6 here. So that's a huge difference from that it's possible to work above 40 calories, but it's hard to buy PPE. So let's say we can work on it, but it's very dangerous, and now it's still dangerous, but it's something like 4 calories level PPE, which is much better to use. Also, the panel itself is on the edge of 1.2 calories. So probably if you step back 10 centimeters, it's below 1.2 calories. And this will stay the same. Also medium voltage will stay the same. Just to show you the comparison. So you can see that we drop from 48 to 2.6, 49 to 2.4. It's a huge difference, to be honest. And that's why we decided to implement it on site. Because when I went through results, I found, okay, that will be the best solution to clear the problems. Also, there was one thing, maybe I can stand back, because we didn't have an access to it, but we can connect the signal back. And because of the fuse used in medium voltage, it was a bit tricky to implement anything else. So this is a separate system that will fix a lot of issues with generally from Arctech's point of view, but also from selectivity. Because as you remember that selectivity and generally safety and selectivity, or arc flash and selectivity, is a compromise. So all we would like to be fast and safe from Arc flash point of view, or we would like to have a bit more time for selective operation. And when we use arc flash relay, we don't have this problem because it operates aside. So it's like a separate system. So that was the main goal why we went through it. Conclusions. So I had a few questions when we were doing this project. One was that, from conclusion point of view, settings improvement is always first choice for me because it's straightforward and easy to implement on site. Sometimes by electrical engineers on site by themselves. So that's always first choice for me. The Akash relay, it requires a bit more investment. It's a very good solution for high energy areas where we have a problem, especially if it's combined with medium voltage tripping signal. Sometimes it's not possible, but if it is, that's the best choice. New switchgear. So, as I said, the replacement was done before I was asked to do ArcFair study. So it might be easier and cheaper to implement other solutions or this solution with Akash Relay if it would be done in design phase. And it is generally recommended to do it this way. If you think, okay, we are going to replace everything and then we do Akash study, you might be surprised that at some point you have to invest extra money. So it's better to do it before you do anything. The second thing with new switchgear is related that what I hear very common. It is new, so it has to be safe. And it's not always true, as you can see on this example. It was like 50 calories because it generally was replaced 1-to-1. And of course, not everything. From shock hazard point of view, it's for sure much safer than the old one. But it very depends. Don't take it for granted that if something is new, it has to be safe. It doesn't work this way. Bus duct. Overall, all the bus ducts, actually the final bus ducts on the system that you've seen on the first slide were below 1.2 calories because they were generally below 63 amps and was quite nice. The main bus duct was surprised because it was motor operated, probably because it was on 4 or 5 meters level, height level. And from operation point of view, it was surprised because it was good. It's more like engineering controls measures where we can put people further away and they can operate it remotely. It was perfect. Even with if we will keep 17 calories there, it will not be a big issue. But it was quite easy to implement it to reduce the energy. And I had a few questions like, because we had the clutch. So what if clutch would be closed when the transformers work in the parallel operation? It was not normal operation for this site, but what will happen? Can I buy just 70 calorie suit and forget about everything? Can we switch off from medium voltage switchgear, for example, instead of low voltage? Because it was internal classified, if you remember. Can we consider medium voltage switchgear upgrades with digital relay? Because we had medium voltage fuse and maybe we can install something different. So for few I can answer now because for the last one, the medium voltage relay fuse changed to digital. It was a problem because it was not really customer switchgear and they replaced it a few years ago. So it was also relatively new. 75 calorie suits will not solve every problem. Of course, it will protect you, but it's a last position in the hierarchy of control. So we prefer to reduce the energy instead of providing just PPE to match the energy. That's why I put a lot of focus on recommendations. Switching off from medium voltage switchgear, it was the same problem that switchgear was outside of the site physically. So you have to physically go outside of the company to make the switching arrangement or generally switching actions. So it was not really flexible, but technically could be done this way. And the clutch open close. So this is something which I would like to show you because I went one step further to check it. So there was a clutch which is motor operated. Of course, it can be closed. Normally it's not in parallel, but it can be, let's say. So if this will happen, logically you can expect higher energy, because why not? So just to give you an idea, this is the 2 extra scenarios that I did for the with clutch closed, and this is the rest. So if you compare ACFAS with clutch with open, you see it is generally going up, something like 80% to 100% up, which is quite logical, which is almost 2 transformers instead of 1. But with the settings improvement scenario, you can see that the line side is not really going up that much. It was 48, it's still 48. And you might ask why. And it is something related with the 2-second rule that we use in the model. for the final results. Probably you have a question, what is 2-second rule? So just to give you an idea, this is an artificial topic by NFP70, which is called escape reaction time. So if you have an arc flash or some kind of accident, there is a bang, you have reaction time, I don't know, 1 second, and then you start to escape, which is again 1 second. It might be different, but in total it should take approx 2 seconds to escape. So you not stand there and don't look on the arc burning and burning you, but you escape as fast as you can. And that's the whole, for me, whole story behind it. Of course, it was studied how much it takes. It's not taken from out of blue. But what will happen if you remove this? So I did one scenario without, or 999 seconds. I think it's like 15 minutes, something like this. And then you see that actually there is a huge difference. So with arc flash relay, because it's fixed on 55 milliseconds, something like this, it's 3 calories. With 2 seconds rule, we have 48, but without the rule, so we will leave it until the device will trip or not, we see something approx 1000 calories per square centimeter. So this is not practical energy. That's why we have a 2-second rule. Because, you know, power over time is energy. So if it takes quite a long time, it will be huge energy. Of course, everything will be burnt before, and yeah, and it will stop probably earlier, but you never know. Why we use it? We use it just to normalize, set the results a bit. So if you don't have any data, and you might see it very often, if you don't have any data, you might use 2 seconds rule to put limit on time. It doesn't mean that something will trip in 2 seconds. It just means that it will escape in 2 seconds, and this is still burning there. It's not really recommended, but you might use it in the studies sometimes. What you can do, as I said, because we talk with ArcTech, and they have very nice arc quenching system, which is IQ1000. If you have a question what quenching system is, very simple, and you might refer to ArcTech webinars, but there are more systems like this, but you can refer for the webinars to see the details. But this is generally a device that will create a 3-phase fault. So it will detect the arc like everything else. We got the signal, yes, we detect the arc. And now instead of only sending signal, we try to be as fast as possible. So this whole system will react in less than 4 milliseconds. So this is very fast. And will create the 3-phase bolted fault or short circuit in the system. And in the place of the short circuit, there is no voltage, or voltage is very, very, very small. If there is no voltage, there is no voltage to sustain the arc, and the arc will disappear. Just like that. So it is more complicated, most likely, but this is very simple concept. And if you have this, the only thing you have to do later, you have to send the signal to the breakers, which will operate in 50 milliseconds instead of 5. So they have to de-energize the system, because now we have a 3-phase fault in the system. Difference is that the arc flash is dangerous because of the thermal energy, but short circuit, this is something we designed switchgear for. So you might have 65, 80 kiloamps 1 second, and the switchgear will withstand mechanically and dynamically this kind of current. That's it. So there's no problem with it, if it's rated properly, of course. And I'll show you the next video from Mika, which is very nice. And just to give you an idea, this is the quencher. So that's the device that actually create the 3-phase short circuit. This is the connection here. So it will put it together. And there is a wire, you don't see it, but there is a wire to initiate the fault. And the doors are open, and you can actually see this, what's happening. That's it. So that was 30 kiloamps, 730 volts, 4 milliseconds. I recalculated back to be something like 0.1, 0.2 calories per square centimeters. So very small number. And we are at the end, because that's it for today. So we have now we will jump to Q&A session. Before we go to it, I plan one more webinar for June, and which will talk about the common myths. So I'm still looking on the topics for the webinar, so I have prepared, but I play with it a bit. So the next one will be about the common myths, because I see there's a lot of discussion about it. Then I hit the holiday break, and I'm back in September with webinars because I'll be working, but at least I'll be back in September. Again, feel free to go to my website, subscribe to newsletter so you can get all my mailing list, so you don't miss any webinars, or you can follow up everything else. You can also subscribe to LinkedIn because I will copy it there, and everything I will upload to my YouTube channel. So now we have a time for Q&A session, and if you have a questions, feel free to write it in the chat box. So I'll actually go there and see if we can have something. And I don't see anything, but let me check Q&A. Okay. This is a question from Medhat. Let me read it. For sure, using arc protection relay is extremely helpful to limit and control the arc inside switchgear board, but at the same time, we need to ensure that all the operational parameters to be healthy all the times. I always do prefer to have independent solutions as basic solutions like the design itself for switchgear compartments and arc paths to be away from the operators and other adjacent equipment. What do you think? So I think it's more like if we invest in hardware, like a switchgear, or we look for hardware, software, like the relays and all the other solutions. So generally, I can tell from practical point of view. So we work with what we have. So if we can, if we have an arc-rated, arc-resistant switchgear, that's very nice, but you have to keep in mind that there are some rules behind it, that everything has to be closed, sealed, and that's perfect. It's a little bit different on medium voltage than on low voltage, because it's very likely that on low voltage everyone will open it live, and on medium voltage it's a bit harder. On the other hand, I very like arc flash relays because they are separate system, easy to test, and no one's going to change anything in it, so it will generally work. You test it and it works. There was a previous webinar, but we might also implement some special adaptive settings on medium voltage system. So you might have not one, but you might have few solutions that will work for you. And that's so I try not to rely only on hardware as it is, that someone will tell me that this is perfect safe, but there is nothing to prove it, or it's very easy to override it. I hope this answers your question. What else we have? There's only one question, so I'm waiting for more people to write questions here. What I can say, for example, from my perspective. Okay, here it is. Maybe I missed something. Hi, AIS is constructed to be arc resistant, so is there any risk of arc flash when the doors is closed, or we are talking about possible working on exposed parts? I think you say air isolated switchgear. So if you have a medium voltage switchgear, which is internal arc classified, there are some, of course, for the test, like 16 kiloamps, 1 second, or 20 kiloamps, half second. So you have to be sure that you are in this range. So if everything is in this range and everything is closed and sealed, and most of the, I would say 99 on 100 from medium voltage switchgears now is impossible to open live. So you have to override it somehow mechanically, but it's very hard to. Then technically there is no risk from arc flash if it would happen inside the enclosure. And since you cannot open the doors, you are safe to operate. So that's the whole thing behind it. Technically, I saw not the paper, but the book almost, about this discussion about the internal classification, where you can look into some more details about you have a arc flash chamber or arc flash coolers, or you have a cable chamber where you release all the pressure, everything inside this place, which seems to be that the longer it is, the bigger the pressure might build up in the panel itself. It's a specific topic, but I saw this request last month. So technically everything is tested, you are in the range and it's internal arc classified, then everything's supposed to be okay. But and you cannot open the doors unless you really work on exposed parts. That's something, and then you don't have it. You might forget about it. You treat it as there is nothing. Does arc quencher need any AC or DC connection for its operation? As far as I know, yes, but there is Muir somewhere here, and he might answer you, or Arctech, more details. But as far as I know, it's a spring operated. It is fast, but it needs supply. And I think we had the same issue here, that we need to install some UPS for the backup operation. But this is a good question from very detailed point of view, which I think Arctech will answer better than I, because it really depends what kind of system it is. What else we have? I can add from my perspective that when we work on this project, and this is something which I also will drag in my next webinar, that there are some myths around it, and I blame a bit of sales for it, because you hear internal arc classification, you hear arc rated switchgear, and closed doors, and it's new, and everyone says it is safe because it has to be safe because it's new. The problem is that it really depends how you are going to use it. There's a lot of things behind it. Also for arc-rated low-voltage switchgears, when you use them, you have to be sure that everything is closed, everything is sealed. No one is testing the switchgear with one lock closed and the rest open. So it has to be done as in manual. And you have to keep it in mind that the same is for the internal arc classification switchgears. Everything has to be as it is set in the manual. So if you can manually override something and you leave the doors open, you don't have this classification anymore. So you might need your PPE. And the ARFA's consideration for battery energy storage source. So this is a whole topic for the next webinar, which I think I might be doing. So we will talk about the DC arc flash as we speak. And I have a different project for data center where we have UPSs with big battery panels, and the same battery energy storage is generally the same. Very similar is PV systems or the inverter-based sources. And this is a very interesting topic because, as far as I see, it's overlooked a bit. Also, different problem, but same topic is with EV cars. So you might see systems which are 750 DC now, or even higher, 900 volt DC systems. And they will cause a lot of issues now from shock hazard point of view. That's one point. And also from arc flash point of view, which is a second point. And probably more than this, but looking on my field. So yes, I have some consideration regarding battery energy storage sources, and they will be very tricky part. It very depends now on the design. If you design it different way, it's hard to solve. It's like a whole webinar for me to write. But generally speaking, they are very prone to the design, mechanical design, and also how you design the cabling, how you design the protection, where you put the protection close to the source or in different panel. If you try to make common DC bus, as I see very often in UPS systems, or you supply each set individually, so it makes whole big difference generally for the results. Sorry, I cannot answer straightforward, but yes, I have a lot of considerations for it. Yeah, I see the Miko wrote that AQ1000 needs 24 volts DC supply. Thanks for that. And you can get all the informations later. Yes, I will share the webinar, Amlila. You can, if you will be on the mailing list, you'll get the email with the link. If not, you can look it on my LinkedIn or YouTube channel directly. What else we have? So where we are close to the DC systems, I'm planning to make the webinar hopefully this year after holidays, because I saw there are a lot of issues with the UPS system, batteries, and how to approach it, generally from the RFID point of view, but also shock hazard. And I got some requests regarding electric cars, electric trucks, which is a much bigger system, and battery storage, which I've seen on LinkedIn recently for some nuclear plant. They might be relatively small, but they also might be huge system. And we did in past, I think for Fluence or IES, if I remember correctly, also grid frequency support systems, studies for it, and it is very interesting topic, and there are a lot of solutions that you might use there. I would say there is no one straightforward answer because the systems are not unified really. What we have here. I think I saw something, but it lost. Anything else? Any question? Feel free to ask. You can always ask me directly on LinkedIn if you think it's more appropriate. So no worry with this. I try to always answer as far as I can. Sometimes it takes 1 or 2 days because I'm physically traveling somewhere, or the question is more complicated than normally it is. It might be easier to call me. It's generally open. Okay, I think that's it for today. So it was very nice to meet you all and see all the people. Again, feel free to subscribe to the newsletter because I think that's the best way how to let you know about the upcoming webinars, and that's the only reason why I created it. See you next time. So the next one is in June, when we talk generally about the common myths, so misleading information and so on. So I'll try to make the bigger list of all the things I hear and I see, and I think people are losing the idea what's happening and why it's happening. Again, thank you again for joining me today, and see you next time.